Welcome to the 183rd monthly meeting of the New York Linux Users Group, back on a regular schedule and a regular numbering. Tonight we're going to be hearing from Senad Palislamovic, who will be talking tonight about SDN, how open source software is fundamentally changing computer networking. I'd like to say how much we appreciate Bloomberg allowing us to use this great space and for sharing the food, the drink, making this a great space for us. And thank you to everyone who's here for taking the time to come to our meetings. Now, in addition to our space sponsor, Bloomberg, I'd like to thank our other sponsors, past and present, IBM, Canonical, Brandor Group, Google, and O'Reilly Media for their past support and continued support. In addition, Nilog would not be able to function without our many volunteers. All you know who you are. Without their contribution, we wouldn't be able to do this. All right, so software-defined networking, Senad. How open source software is fundamentally changing computer networking. Again, please feel free to ask questions, clarifications, etc. Just come on up.
Thanks. Thanks, Peter. Thanks, everyone. So I was expecting he's going to butcher my last name, but he didn't even attempt to do so. So Senad Palislamovic. It's fairly easy. One thing to note, we discussed this back and forth in terms of the questions. Typically, you guys leave the questions for the end because this is highly technical talk, and we were told that majority of audience is not network savvy, so there's a lot of terms, a lot of terminologies. We are encouraged to ask questions as we go along. However, what we're going to do is not to let you ask questions immediately, but I have 3 different stops. There's a networking section, then there's SDN 1.0 and SDN 2.0. So if we can align the questions after each of the segments. So networking questions after network 2.1, and then SDN after 1.0 and then after 2.0. Cool? Perfect. So first of all, disclaimer, as I've seen you guys do. Whatever I talk tonight is really my own belief. It does not represent the views and opinions of my own company that I work for. I myself have been involved with SDN for about 2.5 years now, and prior to that, I've lived in networking world, enterprises, service providers for about 15-20 years. Okay. So what is SDN? I think by now, every Tom, Dick, and Harry have their own version of SDN, and you've heard millions, and you've read tons of different articles, and they all talk about different opinions. So if I come and tell you, I'm going to give you the best opinion, I'm going to just be another Dick. That's not what I want to be. The idea is, since I lived in that space for about 3 years, I can guide you through the evolution of SDN, where SDN started, where is it now, and where I believe it's going to go forward. And then you yourself can derive opinions what SDN is and what is it about. So, as I said before, to understand SDN, it's really about software defining networking. So you have to know ins and outs of networking. I'm talking about not just networking as a concept, but the network devices, network elements, what we call routers, switches, optical equipment, DWDM, shelves. And because of that, and the way we were told is that most of you guys are not networking gurus. I believe audience comes from sysadmins, DevOps, programmers. We're going to guide you through some networking fundamentals before we approach SDN. The reason for that is, some folks make a claim that SDN existed 20 years ago. We had SNMP protocol. It was a software, and it drove the network elements to do certain things. So you can say that SDN actually existed 20 years ago. So that's why we're going to actually go into details of networking to understand what SDN is all about. Okay. So sometime after ARPANET, great brains have decided that anything that has to do with networking should actually be split in different layers. So they came up with this standard approach, OSI 7-layer model. It's a great idea because it allowed us to actually develop and evolve independently each of the layers. And as long as you as a developer, whichever layer you work on, when you write your stack, hand off the packet or frame or the piece of information according to certain standards, life is good. We can understand you. So what they came up with is a 7-layer approach where if you look at here, so I don't typically live in these layers. This is where application guys work, but I can speak somehow about them. So the layer 7 is application. This is mostly where any applications that we work with, GUI itself lives in. And then as it needs to access the information data, whether it needs to save it or retrieve it, it goes through presentation layer. Typically file formats or encryptions are considered to be presentation layers. And then as I access that and I need to connect myself to something else, typically these connectivity endpoints live on each layer. So my session layer connects to your session layer and vice versa. My transport layer connects to your transport layer. So typically when I talk about sessions, I consider, and I may be wrong on this, but if I have two browsers open going to the same website, there are different session IDs. So therefore I can differentiate one from another. And then as I stack the session ID inside of that, around that payload, I encapsulate that information into a header that's added by transport layer. And the protocols that live, so this is where we networking folks live in, these 4 layers. So protocols that live on transport layer are typically TCP and UDP. And we distinguish the identities by TCP UDP ports. So if I set up a session to a web browser, I can take a random TCP port and I talk to port 80 on your end and vice versa. And then what I do is I take this TCP header and then I pass it along to a next layer, in this case networking layer, and I need to encapsulate the IP header around that. Network layer is all about path determination and logical addressing. So every entity in a network has an IP address, and the network layer deals with building the end-to-end paths. And there's an entire industry that's built around this network layer here, routing protocols, tons of them. And I know people who spend their entire lives just living in this layer itself, right? So the fact that we have modularized the system actually allowed evolution of each of these layers independently, and it was a great thing to do. So anyhow, once I encapsulate my packet or my information, what we call datagram, into the IP header, and now we call it packet, I pass it on to my next layer, in this case, data link layer. This is where things like MAC addresses live there, if it's Ethernet. So I add the MAC address around that IP header, and then I pass it on to the physical layer, which is just ones and zeros, bits. So this is a network layer in summary. So if you really look at us as a network guys, we live in these 3 layers. And if I look at the history of networking, where we started and where we are today, probably about 20 years ago, I'm sure all of you have heard of terms like T1, E1. I know when T1 came to my office, we were like, yeah, we have T1, we can go to the internet. Yeah, now it's like you laugh at it, right? So we started with TDM access, T1s, E1s, eventually, core links were T3s. And then as time passed, now you have T3 in your office, so it's cool. And then, afterwards, the optical gear came into play. So from digital, we came to the optical transport, which gave us faster pipes. So SONET came along, and packet over SONET, even faster stuff. And now, the latest and greatest technology in optical, it's DWDM. So we actually take entire, whether it's packet or frame, and we dump it on optical fiber. And we have accomplished to split the single fiber strength into different channels using different wavelengths. So now you can do like 88 or 96 channels on a single fiber strength, right? So this gives us 96 times whatever that bandwidth is across. So it's a great evolution in technology. And then from the layer 2, data link layer, we had in the WAN links, we had ATM and frame relay. Those are packet switch networks. So service providers used to give you a VPN that's based on ATM or frame relay. And, time passed along, Ethernet came along. In data centers LAN, Ethernet was always predominant layer 2 technology, and the cost has allowed us to move Ethernet to the WAN. So now if you look at even your service providers' connectivity points, or even the cores of service providers, they're built based on Ethernet. So we started with 10 megs, then we moved to 100 megs, gigs, 10 gigs, now we have 40 gigs, we have 100 gigs. So if you look at service provider core, it's actually n number of 100 links ports going up. So Ethernet has taken over the world when it comes to layer 2. And then in terms of the layer 3, right, we had IP routing, and then as time has passed, we evolved. So there's some discrepancy about MPLS, whether it's a layer 2 or layer 3, layer 2.5. It's a label that sits on top of Ethernet frame, and it's before IP header. Fine. But this allows us to build now different types of VPNs. Before it used to be ATM and frame relay. This technology dies, but now we can still build VPNs using MPLS. So now if you look at the networking world itself, state-of-the-art technologies are in WAN, we're talking about MPLS-enabled routers, or in LAN, we're talking about, or data centers, we're talking about Ethernet switches. This is the state-of-the-art. So quick question, am I loud enough? So in order to understand the reason for SDN, or where SDN brings us, now we need to dissect what routers and switches are and how they work. Why is that relevant? Because the whole SDN has actually chipped the market from routing and switching vendors. And once we decouple this, now you can see that the whole new arena of vendors and the way you build the networks have come about. So if I look at router itself, and this holds true for switch or router, there's a CPU module, we call it brain, right? And its job is to build network topology. So whatever information I have, I tell my neighbor, you tell your neighbor, you tell your neighbor, and now all of us talk to each other and we build a network topology. And that's the CPU's module job. And that topology, we call it RIB, routing information base. I stored my at the end of the day, IP prefixes. You might be advertising 137.190, you might be advertising 172.16, you can be advertising 10.10, and now I stored it in my RIB and I know how to get to these networks. The second element of the router is the actual forwarding chips, line cards. This is where you connect your physical ports. So your laptops, your computers, servers, they get connected here into physical ports. And typically these line cards have ASICs, so proprietary chips that allows forwarding of the packets, and they're interconnected between each other through the backend fabric. And typically the interconnection is a class-based architecture. Class means that every line card is connected to every line card without any bandwidth issues. What I mean by this is, if this is 10 by 10 line card, so I have 10 times 10 gigabits, so it's 100 gigabit line card, the connectivity points between this line card and every other line card have to be at least 100 gig in a bandwidth wise. Actually, typically what happens is there's a speed up in the back end anyways, so the fabric connectivity is typically 2 times what is required just to get the right timings and stuff like that. So the second part that we didn't talk about is the fib, concept of fib. So now I said my CPU builds a topology. Now a CPU can have different views of topology. Maybe you can be advertising 10, 10, 10, 10, and you could be advertising 10, 10, 10, 10. So now I have 2 ways to reach that network. The way it works is I actually go and select which one is better. And this is what routing protocols allows us to do. And once I select which one is better, I only download the right entry into my fib. So this is routing information base, this is a forwarding information base. Here I install all active routes or all active paths, if it's a router, if it's a switch, MAC addresses, destination-based MAC address lookup. So what these ASICs do is when frame comes in or packet comes in, they look at what destination IP or destination MAC address is, and they match it with outgoing port. Says, okay, This network lives on port 10. This network lives on port 11. So this is what ASIC does with the help of fib. And typically, in the router, the process of RIB downloading the information to the fib is done through the proprietary protocol. Every vendor, Cisco, Juniper, Arista, Alcatel, anybody else, they all have their own versions of protocol, and they also have their own ASICs, and they also have their own lookup algorithms, where they're different from each other, right? The way I look up in my table, and I hash the traffic, and I figure out what is the way to go out for this specific packet. This is typically proprietary. So now what has happened sometimes 2000X, 2003, 2004, is different vendors came on market building ASICs. They're scaled down ASIC versions, so I don't have all the fancy things that my Cisco ASIC does or my Juniper ASIC does, limited subset of features, but the cost point is much better than what I have to pay for Cisco. So if you look at a lot of switching vendors and a lot of switches being deployed already in data centers, they're all built from off-the-shelf ASICs. So nobody actually now, when it comes to data centers, nobody builds their own switches. They just go off the shelf and buy the ASIC, typically from Broadcom, or now even Intel is going into their business, and we call it merchant silicon. So now what has happened is, I think actually I'm not going to go into that yet because this is going to be SDN element. So this is just for us to understand what's happening in the market, right? Control plane. We talked about it's a brain of the router, and it creates the paths. And the way it does it is through what we call routing protocols. So I'm not sure if you've heard, but there's a thing called OSPF, BGP, ISIS, spanning tree, Trill, whatever. Those things help us build topologies. They find the best paths to connect certain elements. So if you talk about enterprise network, we typically use OSPF or ISIS, right? But if you talk about connecting my network to your network and your network to someone else's network, and connecting to service provider, and service providers talking to each other, is typically BGP. So if you look at internet, it's just a bunch of networks talking to each other through control plane to set of protocols. And this is a job of CPU. So this is a control plane. There's a concept of data plane, which is my payload, my actual data that I'm sending through the router. So control plane is built, you can think of it as out-of-band communication. I'm talking to you, and it's not my customer traffic going to it. It's just me talking to you, and we are talking and negotiating what the networks we should be advertising and things like this. Data plane is actual customer traffic. It's the traffic that I need to send through my routers. So control plane builds the topology. Data plane encapsulates the customer traffic into specific variables, whatever those are, depending on the layer 2 technology. So if it's Ethernet, it puts the Ethernet MAC addresses, destination MAC address. If it uses VLANs, it puts the VLAN ID. If it builds an overlay on top of the Ethernet VXLAN ID, or if it's a MPLS network, service provider network, then it uses MPLS or MPLS labels. So ASICs are programmed to understand what label value is supposed to come in and where they go. So if packet comes in with the label 10, I know its outgoing interface is interface 15. Or if something that comes in with VLAN 51 and specific destination MAC address, I have it in my entry and I know what to do with this. So this is a job of data plane and MAC lookups in the FIBs. This is just an example of one. And then the third element that makes network is provisioning elements. So how do I make my router talk to your router? How do we actually negotiate stuff? So which means I need to go in to my brain and I need to enable certain elements there. So I need to tell it to speak BGP, and I need to tell it to whom to speak the BGP or OSPF or anything else. And what variables within these protocols I should be using to talk to my neighbors. And similarly, when it comes to data plane stuff, what VLANs should I be using on which ports? What MAC addresses should I allow or I should not allow? So all of these things that my router or switch should be doing is typically configured through OSS systems. So it could be GUI based, or it could be config through the CLI, or through certain syntaxes or scripts. So all these three things make network. So if I put them all together, like a network stack, on top of it there's always OSS and configuring of network devices. We call it management plane. And then there's a control plane where all of the brains talk to each other and they establish topologies. So for example, MPBGP. And then there's a data plane that we all negotiated what data plane we should be using for the actual customer traffic. So data plane. With that, I think we passed networking. So I'm going to open up the floor for network-specific questions regarding what we just talked about. If there are any, go ahead.
So please come up to the microphones.
Yeah, please come up to mic.
You guys don't have to raise your hands. Just come on up and, if you have any questions or anything you want clarification on.
My question is about, what about, software as a service when you're trying to do networking, when in the cloud, how the cloud is changing the networking part? How can you verify that everything that you're doing in the cloud is correct through the network?
So we will talk about it after third session. So I've split my talk to now SDN 1.0 and 2.0. So we'll mention cloud over there, so I'll answer your question. I don't think you're going to have a question afterwards, but if you still do, I'll answer the question after third session. Any other questions? Okay, we're going faster than we thought. So I'm sure all of you have heard these terms. OpenFlow means SDN, OpenFlow controllers means SDN. It's not really SDN, but OpenFlow as a concept, as a protocol, has enabled us to move into this direction, has triggered the change in network industry to move toward SDN. But OpenFlow, it's nothing new. We actually already have these protocols, and we'll talk about it later on. They've existed since way back 1996 when Juniper put out M40 router that had separate control plane and data plane. So all these things existed. Now just the hype changed the industry. Open source projects, I'm sure you guys are aware about a lot of network open source projects that are out there. All of them have actually contributed to the SDN, to evolution of SDN, and they're still part of that SDN evolution. White box switching. How many of you have heard about white boxes? Anybody want to take a stab? You can go off without mic or...
x86 with a bunch of ports.
Okay, that's one way. Perfect. It could be x86 or it could be Broadcom, the actual ASIC that's bought by somebody, and you just put the SDN controller on top of it and you make a network device. Absolutely, that is the case. So this...
Commodity hardware.
So merchant silicon, Broadcom equals commodity hardware. Sorry for the terminology here. We vendors like to use term merchant silicon because we buy the silicon, right? But yes, it contributes and it's part of the SDN evolution, but in my opinion, all three things here that we just listed are sort of completed their job, meaning they've done what they needed to do in the industry and bring us to a certain point, but I don't think they actually matter anymore going forward. And you'll see later on why do I make that claim. Now, other elements goes to your cloud question is about network virtualization. You all heard about systems virtualization, virtual machines. Now we are at a point that SDN enables us to build network virtualization and enables us to build network as a service. So within the cloud, you have different applications as a services. Now you can attach to it network as a service. And we'll talk about all this into detail. So what does SDN do for us? Many things. The most important one that we started, that was actually, I guess, a starting point of SDN and going into the direction is reduction of the cost. And the reason why is because those monsters, a Cisco, a Juniper, a Alcatel, killed us with their margins, and their equipment is so expensive, so I had to figure out the ways to cut into their margins. So yes, SDN is there to reduce costs, but in the same token, it needs to improve utilization of the network ports, because as you see today, they're only at 30-40%, no more than that, utilized. And then it needs to help us with automation. If you look at the way networks are built today, they are not automated at all whatsoever. And I'll tell you a joke in a second when I get to that slide. And then it needs to get to the motion of the cloud. And if you look at everything in the cloud, it's self-service based. You just go to Amazon, you click on it, you say, I want this and this and that, and shopping cart, buy, virtual machine pops up, and off you go, right? Or even, as you saw at last presentation, now with the containers, even if it doesn't take that much, virtual machine still takes time to spin up and whatnot. With containers, it's like 1.5 seconds and you're up and running. So SDN will bring all of this to a table when it comes to the networking. But SDN itself, because you will ask, you get asked this question a lot, it's all about money and the bottom line of our infrastructure. And it has always been in our industry, I'm talking about networking industry, that only things that survive as a technology and that take off and are still around if they make financial sense. If they don't, they eventually die out and people forget about them. So if you look at Silicon Valley, millions of dollars being put to different startups all over the place, and then only 15% of them survive. Other 75 go away because they don't make sense. We don't make money or we don't save money with that technology, whatever technology is. So from my perspective, SDN does two things. It saves us money, so it reduces the cost of CapEx as well as the OpEx. Okay, so I dubbed it as SDN 1.0, which is CapEx reduction, and then OpEx reduction as well as innovation and getting more revenue out of the network is SDN 2.0. This is my own terminology. You'll see it through the presentation. My own opinion. So if you look at the network architecture that we looked at before, right? We have a brain, we have line cards, we have a backend fabric, we have a guide provisioning stuff. SDN 1.0 really targets this protocol here and splits the system into the two. And SDN 2.0 deals with provisioning and automation of your network. So SDN is a variable, as a cost variable. So like I said earlier, if I look at all of the routing vendors, they're high margin equipment, right? And if you dissect it, there's just a forwarding ASIC and there's some CPU running over there. So idea was, actually, sorry, I have one more here to pick it up. Okay, perfect. So back, I think it's like 2011, beginning of 2011, Casado with a bunch of colleagues out of Stanford came up with OpenFlow protocol and said, I'm going to change the world. If you look at what OpenFlow is, all it does is said, I'm going to put a controller and I'm going to install the flow entries into my forwarding tables, whether they are software run forwarding tables on x86 or they're on the line card of Merchant Silicon or Broadcom, right? Well, like I said before, way back in '96, we've split control plane and forwarding plane. We separated the brain from the line cards. We just put them in the same box. But if you look at first M40 router, it's actually Intel motherboard with Intel CPU running here, and then this is proprietary ASIC. So that job has done. This is nothing new. Only thing that changed is that he has standardized this process and built the OpenFlow and build the flow table that's generic flow table that's moving industry, so everyone in their ASICs or in their virtual switches and x86s uses the same algorithm to look at the flows. And if you go down that path, now you can split those two components as individual components. We can buy them from different vendors. So now you can take SDN controller for vendor A and buy line cards from vendor B. This is what OpenFlow brings to the table. Standardization of what I call rib to fib protocol. So this allows us to buy off-the-shelf line cards, right? It's worth mentioning that apart from OpenFlow, there's other protocols around being used and sort of trying to get into the standard. One of them is OVSDB. Having said that, because of the hype and the industry adoption of OpenFlow, I certainly believe that OpenFlow will stay around. The reason why is if you look at every hardware vendor has built OpenFlow interfaces, and all of the SDN controller development, these guys, is about building OpenFlow as a southbound control plane toward the line cards. So it seems like OpenFlow will stay around. With that, we need to thank all of these guys here because they have the open source of networking, because they have actively contributed to this SDN evolution and OpenFlow itself. One thing to mention is, and we'll talk about it later on, but anything that has to do with the networking, and I remember Brian mentioning this statement, has to go through ITF. So all of this BGP, OSPF, or different protocols that we use to talk to each other, they have to be standardized. They have to have somebody that says, yes, bit 17 from byte 48 means something, and bit 21 from byte 7 means something, right? This is the standard by the industry. So everything we do has to be compliant to IETF, so even open source itself. And then from the groups, Open Network Foundation are the guys who actually build OpenFlow, right? Then where we are going as an industry from the SDN perspective is those two elements, Open Daylight Project and OpenStack. So when it comes to the SDN controller development, as it is today, and where is it moving forward, everyone is using Open Daylight Project. And I'll tell you in the next slide why that is and why this matters. OpenStack, when it comes to data centers. So anything that has to do with the virtualization of your workloads, so your servers, any development regarding the networking is going to happen in OpenStack. Now, putting that aside, Open Virtual Switch, they built the first switch-like entity in the software, right? And it's open so everyone can use it. Quagga and Bird have built routing and protocols and open source based way back, I think like 10 years ago or so. And then this is the list of all companies that have open sourced their own controllers and their forwarders. So all of them use OpenFlow. One to point out is OpenContrail. They're the only ones who do not use OpenFlow. They have their own proprietary protocol, XMPP. So because of that, I do not think they will stick around as an OpenContrail. As a different entity, yes, definitely, within the Open Daylight project, but not on its own in the stack. So why do I call this SDN 1.0 and why do I make a claim that it's that? So the purpose of OpenFlow and purpose of standardization of RIB to FIB protocol was to take away high margins from these guys, right? And enable entire ecosystem of white boxes that you can take any off-the-shelf Broadcom chip and take an SDN controller and run the network. So that enabled companies like Cumulus, PK8, Nuage, where I work, to build white boxes and have them controlled with the SDN controller. Arista somewhere in the middle. The reason why I put them in the middle because they come from this space, but their CLI is heavy programmable and it's OpenFlow capable, so they could also be a white box. So somewhere in between. So if there's any Arista guys, don't throw tomatoes at me. But what has happened in the market is because availability of these boxes, all of these guys have now changed their margins and their expected margins. So now this guy sells 10 gig port for $120. Guess what? He sells it for 110. Same way with this guy and this guy. So the OpenFlow and SDN with the controller and the forwarder have done their job. They've eroded the market to such a drastic levels that there's no more room to go any lower than it is, because you cannot get cheaper chip than it is from the Broadcom or from the Intel, right? Which means these guys operate on very thin margins, so there's no more movement here. That's why I say this concept of separation and evolution in this space is done, is completed, right? Couple things worth mentioning when it comes to SDN 1.0 and open source networking. Earlier I listed a bunch of companies that deal with open source, and they're all OpenFlow based. But if you look at networking as networking, it's slightly different than the rest of open source projects. If you talk about databases, if you talk about web, if you talk about mail applications, they're typically stacks. If you talk about networking, it's about communications, me and you talking. So if I want you to hear me, you have to understand what I'm saying. We have to speak the same language. So if I pass on you a bit 7, you have to understand that bit 7 means something. If I say A within the bit 7. So networking is all about horizontal communication, okay? So if you go ahead and build something in your own stack and the rest of the world doesn't agree with the way you build it, it doesn't work in networking, because networking is all about passing the buck left and right, right? So only way you can build things in networking, even with the open source, is a larger community, not its own stack, its own company community. And there are two places to do that: Open Daylight and OpenStack. So if we are building the SDN controller, an open source SDN controller, whose job is to control the forwarders, whether it's a Broadcom, whether it's Intel, whether it's whoever else comes on the board. It's an Open Daylight. We build policy engines there, and we all agree on north and southbound protocols to use. So how we talk to our policies and our applications, and how we talk to our forwarding elements. The second piece is OpenStack. We were talking about data center virtualization, and now doing the similar networking within the servers, within the hypervisors. We are doing it within the OpenStack. And all of the northbound and southbound APIs and network plugins are done in OpenStack, again as an open source. Another reason why those are the only places that you could develop something is the fact that if you look at the spending cycles and the way we build networks, you don't just rip and replace. You have existing network, you have existing workloads. You cannot just go and say, okay, I'm going to stack up 30 switches beside the other switches, and tonight I'm going to just shut it off, I'm going to replug it in, and then tomorrow I'm going to turn it up. That's not how it works. Any company, the way they do networking is, it's a slow, gradual deployment. I bring in 10 new switches, I bring some new workloads to those 10 new switches, I bring some traffic to them, and then eventually I bring the traffic to the new servers, so I shut down these servers, and then I redeploy them somewhere else. And when I do so, I retire my set of switches. Guess what? When I did this, these new switches had to talk to the old switches, which means they had to talk some protocols they all agree, which is, so if you want to build something, it has to be done in an open community whose members are these guys who represent old switches, as well as the guys who represent the new switches. It cannot be a single stack. And one thing to note is, whatever these guys do has to be approved by ITF. And within ITF, there are different working groups. Again, it's not research. IETF is a body that puts a stamp on every single protocol. So for me, networking guy, I can speak to it, but even application guys, even SMTP, POP3, your web, HTTP, your SSH, everything is stamped here, and every single bit means something according to IETF. So whatever these guys develop has to be in accordance to the IETF and their blessing. Another node that I want to talk about when it comes to SDN.1.0, there's this big misconception when people talk about OpenFlow. There's this big OpenFlow controller that controls a bunch of forwarders, and this is how the world runs. So you can ask a question and say, well, what happens when my network grows? Now, do I have another SDN controller? Or does it go to the same SDN controller? And what happens when I have a third? So my network now goes even bigger. So now I have hundreds of thousands of workloads and a bunch of switches. Do I control them with 1 or 10 controllers? Guess what? The backend of each of these SDN controllers, at least based on the original OpenFlow designs, is database. So now I'm at this. Now I have a sync problem, database sync problem. So what happens for? I mean, I'm sure you guys know this better than I do. When the moment I have certain latency between my databases, I think it's more than 50 milliseconds, 1.5. Then I get into locks and issues with databases. So having one controller or even set of controllers that have databases in the back end that they need to be synced to run the network doesn't make sense. And the guys who built network protocols 20 years ago thought of these problems. They're the smartest dude. Even 20 years ago, they're all PhDs, they're computer science, they knew databases. And the reason why they build the routing protocols, such as OSPF, BGP, and the reason why they build distributed state machines is for that specific reason. The moment you go certain distances, you cannot be in sync anymore, so you have to build a methodology to transfer the information even though when you are not in the sync, and you don't rely to be on sync. This is why we have routing protocols. So the whole idea of having one controller control everything, it's not going to work. So in my opinion, OpenFlow controllers, it's really a solution looking for a problem. The claim that's being made is that, I don't know if you guys are familiar with the word, actually, you know what, maybe that's not it. Maybe I'm going too far out. So we already talked about ships in the night problem. Even if this works, if I want to bring it to the network, it doesn't work with the rest of the network, because the rest of the network talks routing protocols, right? So I cannot do swap and replace. I have to interwork together. So only way you can move toward the SDN is by supporting something that exists today and then move it to the new form. So if you look at the architecture that should be laid out and already actually exists in the network today in the mobile space, is some sort of distributed architecture where you have when you have a federation of SDN controllers controlling your network, but using protocols to be in sync, and then having maybe policy and management engine on top of this that controls these SDN controllers. And with that, we'll move into SDN 2.0, I believe. So, anybody has any questions regarding the topics we just discussed?
Your conference is
Could you
scheduled to
describe a
end
little more
in
what
2
the role
minutes.
of the control, you're talking about one controller versus multiple controllers and what the controller does. Can you give some examples of the controllers, any controllers you're familiar with and how they work, and why it is that you think that you just can't, say, have one?
So the controller's job, if you look at original slide here, controller's job is to install the flow entry into the forwarding base. So whether that's a merchant silicon or whether it's x86, my job is to install that information in. So think of it as a CPU module or the RE putting things into ASICs. That's my job. Now, if I have a single controller, if you look at here, if you look at, this is a computer science problem, anything that needs to scale at any given point of time needs to be separated through some sort of hierarchies. That's why in networking protocols you have things like OSPF areas, or if you talk about the BGP, you have AS domains, because you cannot scale individually across hundreds of thousands of millions or of entities. It just is not sustainable from the state perspective. What I mean by state is, if I want to hold every single destination in the world in my table grows like this. That means I have to have X amount of RAM, and if I need to do any changes in my table, my CPU cycles to go through millions of entries versus hundreds of thousands versus 10,000 versus 1,000 are different, right?
Your
So if
conference
you look
is now
at any
over.
computer
Goodbye.
science, anytime we did anything that has to do with the scale, we split it in different domains, and then we build hierarchical systems. So why do I think that SDN controller's job is to have this routing information, if you would, the flow entries, and I need to pull them into the forwarding entries of whether it's x86 or Broadcom chips. So if my network is going to contain hundreds of thousands of routes or millions of routes, I cannot keep that in one database, and I cannot propagate my information at that length simultaneously across all the boards. So I have to split them in multiple controllers, and even for redundancy's sake. And the moment I start splitting these things, if you look at the back end of controller is typically a database, I'm talking about database distribution. And folks have analyzed the state itself versus networking protocol 10 years ago and analyzed that if you want to have a state replicated along large area, physical one, it's better to build protocols to do such job versus have it in database thing, because there's no requirement for you to be in sync in milliseconds intervals.
And I have one other question where you mentioned utilization, where you're talking about 30 to 40% being typical. What in this 1.0 model do you see as being do you see utilization improvements there, or is that for later?
No, it's the improvement comes in SDN 2.0.
So you mentioned that the line cards that support OpenFlow, part of what that did was it standardized on the protocol that they're speaking with the controller. So that has to, I would presume, standardize on the algorithm that they're using. Are there performance implications? Are the proprietary algorithms, what are the pros and cons of those?
So I'm familiar with two proprietary algorithms working for different vendors in my lifetime, and I do not think that there's any performance tax with the OpenFlow tables themselves. I think they're all there the way they're built. I think OpenFlow tables and the mappings will actually work just fine. Only thing is, this is where the question comes, is do we really need to have it the way it is? What benefits does it bring to us? And whether ripping things that exist out there and putting OpenFlow on it will make us any better or not. So this is where the question comes in. And my opinion is that because of different things, not necessarily OpenFlow itself as an OpenFlow, or not the algorithm itself, but because of different elements, the way we are going with SDN, it's better.
Thank you.
So a little bit of a follow-up to that question, maybe. So you're talking about how these vendors have to standardize basically on southbound APIs, but then you mentioned how sort of networking development has to happen within a certain community. Doesn't that seems like maybe there's a little bit of equivocating going on, but that seems to be a little bit of a contradiction, right? So if you're standardizing on southbound APIs, then you can go off and write whatever controller you want and just write the controller to that southbound API to ensure that it implements that southbound API, right? Mm-hmm. Or were you talking about the actual development of network protocols themselves?
Both.
Like-
Both.
Okay, so
Both means if my standardization of APIs allows anybody to consume my SDN controller.
right.
Anybody, whoever wants to have it, as long as they support my protocol, they can consume
In
it.
terms of hardware, network
That's
hardware.
right.
Yeah, sure.
That's right. And in the same token, standardization of me building a controller within a community according to standards allows me now, because this is a network element, it's not a server, allows me to make something that everyone else will understand, because at the end of the day, this line card will send the traffic that's encapsulated within certain bits, and those bits will be frames, and when that bit comes to this guy, he needs to understand what these bits are and how to decapsulate that frame.
Right. So I got that, but like, so what you're talking about right there is network protocols. But you're going to configure your network hardware to implement these network protocols according to the southbound API, right? So everything, as far as I can tell, is hidden.
No. So two things. The configuration happens
Right.
according to southbound API,
Right.
but what that element does
Mhm.
when packet comes out, it's not according to southbound API. It's about what I have programmed it to do. So that's not job of the API, right?
But that logic is encoded in the southbound API calls that you make, right? So
Yeah,
it's
okay.
still like, so what I'm trying to make the point that like it seems as though you can have open source networking development outside of network protocols themselves, given a southbound API abstraction. Does that make sense?
Development outside of network protocols themselves, given the abstraction.
Right.
Yes, but then what is it that you are doing? If you're not building,
You could
Some-
be building better northbound, abstractions for programmers that are more appropriate to certain domains, for example.
Okay, that's fair statement. If it's for the programmers, so it's not for how the rest of the world understands you,
Right.
Yeah.
As long as that understanding is encapsulated in the southbound API, then it seems as though you can do that.
and the protocol that it talks to, that transfers information, yes, that
Okay.
is correct.
Okay, cool. Just wanted to
But
clarify that. And I forgot.
Perfectly.
Okay, I forgot. I had another question, but I forgot. All right, thanks.
I have a question in respect to one of your previous slides, whereby on the left-hand side of the slide you had a list of white box switch vendors, and on the right-hand side, that's it, yeah, you had the black box. My question is this: given Cisco's deployment, or the deployment of Cisco devices as it currently stands, which is very large and all over the world, what do you think things like Cisco One PK or the Cisco One Platform Kit, which is an SDN API that has been made available by Cisco for Cisco devices that support it? What do you think that does, in addition to the fact that these black box vendors are now lowering their margins in respect to the emergence of these white box vendors? What do you think about the emergence of these proprietary APIs like 1PK that will help Cisco retain business? So, for instance, that Cisco shops continue buying Cisco hardware, as opposed to migrating to something, to one of these white box vendors.
Fair question. I think 1PK was Cisco's answer to SDN agenda without being SDN itself. And so what this implies is, if you look at the entire nature of OpenFlow and direction of it, was I can take any controller and I can program any hardware. The whole goal is to separate the two so I can buy best of breed. If I go down the path of 1PK, all I'm saying is you have to use Cisco hardware and you have to use Cisco controller to do something with it. So the question is, will this help Cisco? I think in the shops that are small enough that do not have a large network groups that cannot see to the shades, they might succeed because there's going to be some development there. But I think the larger enterprises that have bigger networking groups, they'll see through this and say, you know what, this is just marketing. This is going nowhere because Cisco is actually contributing to this and building open daylight controller that's actually not using 1PK. So why would I invest in 1PK if even Cisco is building this and Juniper is here and everyone else is here?
Okay. So given that then, do you ultimately, for instance, if you look back 20 years ago, Sun Microsystems, Solaris running on UltraSpark was pretty much the way to go if you were building, say, medium to large networks. For instance, when the World Wide Web really took off, the recipe was to go out and buy a whole bunch of UltraSparks. They're running Solaris, and on top of that, you're running Oracle, something like that. But if you look today at what's happened to Sun or Oracle, however you want to look at it, their customer base has shrunk dramatically. I personally think that the reason that a lot of UltraSpark hardware running Solaris is still in existence is because a lot of people have written a lot of code that run on those systems, and it's very, very, very expensive to port that to x86 64 running Linux. Keeping that analogy in mind, and my initial question in mind, do you think then that like Sun, or Oracle Sun, whatever you want to call it, which is now kind of a niche player, do you think that that'll also happen to Cisco and Juniper and Brocade?
No. And the reason why is because what is there to program on a Cisco device? What applications can I write using 1PK? What is it that I can do with that network? You talk about two different environments. Oracle, millions of applications behind using them. This is a network device. Only thing I can do with networking is what I'm going to talk about in SDN 2.0, which is automated and make it more easily consumable, which is actually happening in Open Daylight. So I actually don't think that there's going to be any velocity behind 1PK or Juniper's SDK writing applications. I mean, Juniper came out with SDK like 7 years ago, and there's not a single vendor out there that supports Juniper's SDK to write the ecosystem around there. So I don't think it's going to be the same as happened to Sun.
Okay.
That's my view.
So given, because for 1PK to succeed, obviously you have to
I'm sorry. I'm gonna ask. I'm sorry. I'm over here on your left. I'm just gonna ask. It seems like we're getting into prognosticating about the future of vendors, and I feel like that maybe is a little bit of a distraction from the flow of that. Maybe we can do this at the bar afterwards.
Okay.
Thanks.
Thank you.
Sounds good. Thanks. And I think I also. I'm gonna think about your question. Sorry, your question about the single vendor, because even if you write your own applications and you want to explore and extrapolate things out of single, SDN vertical, the moment. So what happens is the guys who sit in the back end. Talk about the guys who write checks. They typically, and this is why a lot of networks you have, I don't know how, so I'm not a server guy, so I don't know what happens in server space. But in networking space, almost every single company has 2 or 3 vendors in their network for a couple things. One is the insurance that they'll get the best buck for $1. Means the moment you start charging me a little higher than you should, I'm going to buy more from this guy, or at least I'm going to get the PO. I'm going to send it to you. I'm going to say, hey, he's selling me for this, so I'm going to get your price down. Okay? The second piece is security. The moment something happens, because you're 2 different vendors, right? You're writing different OSPF codes. Yes, they're standardized, but you might have a bug that you don't have a bug. So your bug causes part of my network to go down, but I was smart enough to build my network redundant enough that second path was always going through a different vendor. So your bug doesn't affect him. So when I look at and I build the application like that, my application actually has to talk to 2 different vendors. So I'm not gonna go and extrapolate and put some advantages from the single stack that the other stack doesn't have. Which means my interest would be to whatever I want to have that advantage of, to go to the open daylight and influence open daylight to build something like that I can take it from 2 different vendors.
Sure, but the assumption is that those 2 different vendors are going to be, I mean, I would assume if you're like, okay, so if you're just using Open Daylight, right, and you have 2 different vendors, you're going to be speaking, presumably, the same southbound API to both of those 2 different vendors, right? So again, it's still, you know, standardizing on the southbound API, right?
That's correct?
Yeah.
So that is correct. So what I'm saying is, everyone who wants to succeed has to be part of the Open Daylight. And if you're not part of the Open Daylight, you will not succeed.
I'm gonna okay. I am actually gonna intercede again.
Stack.
No, not that your question is not direct. I also feel like there's a couple more things that are going to open up in the next few slides that maybe will change the conversation.
So we talked about this. Oh, actually, we covered everything. So, okay. So now let's move to the other part of SDN, which is OpEx savings and then new revenues, right? How do we do this? So we talked about reducing costs. So now this is where asset utilization comes into play. And how do I get my network plumbing from above 30-40% to actually 90%? And we'll tell you the reason why that needs to happen. Automation. How do I get from 10, 15, 30 days provisioning to what cloud gives us 1, 2, 3, 5 minutes, right? And the whole model of cloud, which is self-service. I don't have to call anybody and beg you to give me a VLAN and beg you to put some change on a firewall. I just go in and I actually click on this and this and this and just make it work. Self-service like a cloud does, like Amazon does. This is the goal of open, of SDN itself, right? So if you look at today, what happens is compute is completely virtualized. For the most part, our world is moving toward virtualization. Some to the virtual machines, others to containers for the tax that virtual machine gives you. Irrelevant. The goal is that we are driving our servers to 90 and above utilization from the CPU perspective, right? Because we are sure that the way we build infrastructure, the moment it goes the next request, and it's going to bring us above that 99% threshold, I have another server laying around, or I can spin up another virtual machine with the same application so that request can be fulfilled. Now, if I look at network, like I said earlier, it's only 30-40%, right? For the reasons we know of them, right? The one is, in the data centers back in the days, you had spanning tree, so it only allowed us to use one single interface, right? Or even if I look at the WAN use case, I'm talking about the service providers network, because everything is built redundantly, typically they don't override it above 50% because if one interface fails, I have to be able to switch the traffic to another link, so I cannot go above 50%. So what happens is if I'm overutilizing the system and I'm about 51%, I actually have to buy 2 more ports. So then this is running at 1% and this is running at 1%. So this is not perfect utilization, right? And then when it comes to time to get things up and running, if you look at data center use case, what typically happens for so developer wants to test some application, needs some servers, calls up the guy who gets the server, say, okay, you can use server X over there, but before we do that, we need to get you the right VLAN. So I call the networking guy, he says, okay, fine, I have 10 things to do, so I'll get to you in 2 days. Fine. Oops, by the way, that VLAN is closed, there's a firewall that sits in front of it, so I actually need to go and, what do you want to do? Oh, 443 port? The firewall guy says, you know what? We don't open that port on this VLAN. So, and I have to go and have a meeting between security team that says, okay, do we let him to go 443 through it or not? So all of that sometimes it takes like 3-4 weeks, right? And you all know that this is the story that you live in, right? And the goal is to actually do what virtualized networks do, and availability in a minute. So how do we do that? Cloud is bringing that initiative as well, means from moving it 3, 4, 5 weeks, or if you talk about the service providers, sometimes actually to spin up certain circuits in the core networks sometimes takes 2 to 3 months, to be honest. So we need to move it to the consumption level that cloud enables us to do so. So how we do that? We do it by network abstraction and policy networking. So if you look at OpenStack, specifically the blueprints around abstraction says that we need to have application-centric approach to networking. So we need to move away from ports, subnets, and routers, and we need to abstract those elements, and we need to let developers express their desired connectivity for whatever application components they have, and high-level policies that govern that connectivity. You guys should be doing it. And then what we need to do is, and all of that has to be built without any constraints on underlying implementation. So what needs to happen is that we need to abstract networks and network elements away from ports, VLANs, IP addresses, VRF targets, MPLS domains, whatever it is, to very simple in terms like a green and red network. So application guys can understand what's green, what's blue, or what's yellow, right? So what happens is we need to, once we abstract it, we'll build the policy templates that govern that connectivity rules. And then anytime you need to build your network, the policy gets asked about network governance, and the networks that get built can be built by any user out there, because you hide all network complexity underneath that. And what happens is, so typically this would happen when I build a policy. The guy who would build the policy would be a network guy working together with application guys. We know what the governance rules are about network connectivity, and we build policies together, and then each developer on their own can go and build their own networks on fly buttons. So what you end up having is different sandboxes, entire network sandboxes for application guys. So we can have database and SAP and web, totally different networks built per applications. And the way we do this using late binding model. So if you look at, and I'm not the application guy, but I've looked at the designs and whatnot. So if you look at how applications gets developed, right? You first define the source code, then you compile it, and then you only bind it when application actually starts up. This is when you end up locking the registers and using the memory. So there's a concept of late binding. You build things to be used, ready to be used, and then use it at the right time. So the same thing with networking. We need to get to the model of policy-driven network that says we define what network requirements are, we build the policies for those network requirements, we map them onto network services, so using whatever, IP addresses, subnets, VLANs, if it's a VPN, route targets, BGP, whatever that is, if it's beyond, but something that's hidden and is part of the policy, so we don't need to know about it. And then we only use it when we need it, which means I don't have this network running at all time. I only have it running when you need to run it. So you click on a button and you said, I need 5 servers, and I need, let's say, 5 virtual servers for these 5 applications, and they need to be part of the green network, and they need to access internet for X amount of time. And you go in a shopping cart and it says, okay, this means I need to buy network 387. And you click button yes, and we build a network for you. And that network is actually built with the right security parameters, the right IP addresses that are for your specific network 386, with the right context to the internet and right firewall security rules. All of that in a matter of one single click. So what you end up having is you build SDN stack, using policy already predefined and using the control plane and forwarding plane as defined between the SDN controllers. The similar method, and the reason why we're going in this direction, because this is something that already exists out there, and it's proven to work, and it's proven to work at a scale. There's over millions of cell phone subscribers. Every cell phone has an IP address. Every cell phone is tied to a thing called SNMP gateway that has a QoS profile that's associated with me. When I land, I'm going to Chicago tomorrow, so I'm going to land there about 9 o'clock. When I land and when I turn on my phone, I'm not going to call AT&T and say, AT&T, I'm in Chicago, you need to give me a different IP address because you're advertising different subnet from Chicago that you did not in New York, and I haven't paid my bill, so you have to cap my rate from, whatever, 10 gigs to actually not something suboptimal because I'm above my rate. I actually just turn on my phone, and the request goes to things in the mobile space, such as MME and PCRF, which is irrelevant in this case. I don't need to go into details there, but it goes to the policy that says, okay, I have Senad, and what is his profile? What is he authorized to do? What should I give him in Chicago? Is he roaming or not? Is he authorized to do so? And the policy says, yes, this is the IP you should give him. This is a QoS profile because he paid or he didn't pay the bill. And off I go. My iPhone works. So the idea is that we take the same model of policy, abstracted policy levels, and we bring into the networking. So now when you move your virtual machines and you want your workloads to be in certain servers, as they move along, they get the right properties based on the policy abstraction layers. And then what I call nirvana of that is not I only abstract my topology using topology attributes and I hide it from the users, and I use technology attributes. I'm talking about the routes, prefixes, subnets, VRFs, VPNs, whatever it is. I hide that as well and I abstract it. Now I allow all of that in a set of APIs to be consumed by applications. So now this is just me talking future. What I think could happen is now you could actually build networks. We can build applications with the proper latency requirements, with the proper self-healing assessment, with the proper security rules that you actually build in application itself. In the API, you can say this specific application can only exist in a green network, and we as a community, we as an industry, make some consensus, and we bring 300 different colors, and they give them some meanings, and now everyone uses the same colors for whatever that is, and now in application I can say green networks means XYZ, and my application can only work in a green network. And for subset of users, it can go work on green and yellow network, and that's tied to the user ID. So after that, I don't have to have all these policies and configurations on the firewalls, on the routers, the protocols themselves. All of that is abstracted, it's irrelevant. It just sits somewhere in application and it's done through the SDN controllers. This is what I think it's where SDN is going forward. Question was where to contribute. What I believe we should go is open daylight. If you want to work on SDN controllers, if you want to play with them, if you want to develop, if you want to co-develop, exist in that workforce environment, you should download their controller and play with it. And OpenStack. This is where I believe it's more, actually, because I'm assuming all of you guys are, or most of you are sysadmins and work with applications. This is probably the space you want to be involved, OpenStack, because this talks about automation of the virtual workloads and where they are going with the SDN. Questions?
Can you come up to the mic, please?
I can hand mics out if needed.
Your example about the cellular data network, where you don't have to reconfigure the network as a user. My intuition is that the kind of high-level reason that works is because the cellular networks are proprietary networks, and they don't allow user provisioning. I mean, you can kind of hack around it, but you don't even have the capability to reconfigure the network on these devices. So in the public internet metaphor, where you have these software-defined networking layers, each network doesn't necessarily control all of the endpoints, if that makes sense. So like how do you see, I'm just imagining this as this kind of like policy shit show.
So actually, there's nobody out there that controls every endpoint. If you're talking about service provider network, only AT&T only controls AT&T endpoints. Verizon only controls Verizon endpoints. Cox only controls Cox endpoints. And you don't need to have a policy-based networking. You don't need to control all endpoints. You control your own endpoints. You as me as a network admin of Bloomberg, I control all Bloomberg endpoints. And how my application talks within the Bloomberg users is within my own domain.
I
So
just
when
discovered that Bloomberg does block outgoing connections to Tor.
Oh, perfect. So I'm not talking about, but you get my point, right? I'm building stuff within my own domain, and I'm giving it to my application developers, and you can go and build applications for Bloomberg based on colors that we all negotiate should be, and I take away a lot of hand jobs to do what is done today.
Can I see if I understand the clarification on the question, though? It's phones seem simple because it's one device. What happens if you come in as a user and you need to do 20, 30, 50 things and you need to do it over and over again? Does that change the problem? Is that what you were asking?
I mean, that wasn't specifically what I was thinking, but yeah, that's kind of a good example of a potential source of complexity, where like you have a bunch of different networks that have to interoperate, like the public internet does, but the architecture is drastically different.
So public internet only interoperates at BGP level, and the policies that they interoperate are defined in negotiation between different service providers, what you're allowed to advertise to me and what I can advertise to you. So it's not as open as you think it's open. It's actually very controlled. So I don't think that, I wouldn't compare it to the internet, because actually internet is not as free as you think. Internet is just a bunch of service providers got together and advertise their own routes based on their own self-interest. Okay. So it's not just free. But the part that you talk about, the policies, or you brought up element of having more different user sets and whatnot, it doesn't change the game, it doesn't change the problem, and it doesn't change the solution set, because it's all same. I just define many different policies for many different use cases, and based on where you fit with your use case, with your user ID, you get tied to certain policy and certain access and certain network infrastructure.
Yeah, that makes sense. Thanks.
So I have 3 questions actually, and these are strictly related with networking. So first is, do you think SDN, the ability to match multiple tuples on the TCAM, is a threat to OSI layer? Because now we can think of without a layered hierarchy of matching and forwarding. That's the first question. So basically, we don't do a destination MAC-based, destination IP-based, but we can directly do application-based forwarding, right? So do you think it's a threat to the OSI layer, 7-layer model? Second question is, so this is again a theoretical question. It's like we were in the networking space, we were distributed architecture, right? So we were making decisions based on state transitions across the distributed network elements. So now with the controller, which is a centralized controller, now we can easily make a central decision based on computation that we can get, right? So is it a better approach? Of course, no, because it's a single point of failure, as you mentioned. But can there be a hybrid approach where the switches or routers can do their own things, but for heavy computation, go back to the central controller, and then that does the computation and send the route back? Okay, so that's the second question. And my third question, and my third question, and I'll stop, is the OpenFlow controller base, it's on TCP stack. So basically, you need to have a TCP stack to talk to the OpenFlow controller. Is that a basically counter argument to OpenFlow in itself because you need a network to boot off a network. So, thanks.
Okay. So I'll take it backwards, right? So I'll take the first one, last one. I don't think it is, because even once you have an OpenFlow controller, at the end of the day, we dealt with out-of-band management for so many years, so you'll always have it, and you could have your controller program its own rules for TCP connectivity, port 66, 36 or whatever that is, right? So I don't think that's a problem. The hierarchy of SDN controllers. So again, going back to the problem of state and state replication, the moment you grow a certain size of the network, you, regardless of what it is, you have to build a second piece of the controller and you have to sync them. Irrespective of redundancy, you have to do so, right? And you're gonna end up syncing them in some sort of lock-in state and whatnot. And I believe that we as an industry have solved that distributed state problem many years ago by networking protocols. So what I believe it's the right solution should be is that you would have, and this also goes back now to what will survive, whether OpenFlow is a threat to it. I do not think OpenFlow is OpenFlow, and the TCAM space and the way lookups are done is a threat, because what I believe is going to come out at the end is the architecture that's based on open daylight architecture, which will have something like policy engines on the top that govern those access rules, and the SDN controllers that will populate the flow entries of the respective forwarders, whether x86 or Broadcom, whatever that is, and they will distribute the state using routing protocols. So I don't think OpenFlow itself, the ability to do so, because once you go to the application level networking with the virtualization, you don't need to have ability to look at two different parameters in TCAM, because at the end of the day, once I go to application-based routing, I don't even have to have an IP address. I can have a socket talking to the socket within single container or within two different containers. I don't care I don't have to have any levels of granularity that happens in the TCAM and the lookup tables. So I do not think it's a threat, because once the way policy solves that is, whether I look at an IP header or I look at the MAC or something else, it's totally irrelevant. Did I answer all the questions?
Hey, I was just wondering if you could speak to some of the security implications for SDN 2.0. I could see how a more abstract interface could reduce errors on the part of IT staff or network admins, but does that increase attack vectors or have implications for penetration rates for corporate networks?
So I haven't put too much thought into it, so I'm going to just talk on fly here. If we really move to something like this, I think that's impossible, because you're allowing access to your network based on what application chooses should do. But to be honest, I haven't put too much thought into it. So keep it. Let's keep it as that. I don't know. I might be wrong.
You mentioned about provisioning, 5-minute provisioning of network devices. So, for example, in order to provision a device, you need to have a correct asset information.
Can you get closer to the mic?
Oh, sorry. So, in order to provision a device, you have to have a correct asset information. Next, you have to have a correct service information. And a few companies that I've worked in, we store that information in bind database, meaning using DNS records to populate that information and to extract information. What is your industry experience? I guess you've been in a lot of networks. Some people develop their own databases for that. What's your experience with that? How do people store that information, provisioning information, and how do they manage this whole process of population, retrieval, and making sure that it's correct?
So I haven't been in that many places, to be frank, to actually have some broad experience. But I've seen the shops that do things such as Excel spreadsheets, to places where you can store information through DNS, or to places, I don't know if, so how many of here work for Bloomberg? If you look at, actually I don't know, so everyone's outside and nobody works for Bloomberg. Bloomberg has amazing configuration tool actually that's built with zero-touch provisioning, and it's not in DNS. It's its own record database. It's a Perl-based modules. So what happens is Box just comes up and says, "Hey, I am Arista Switch 7609, and I am in New York in." So actually, take it back. It sends an DHCP request. It says, and has some information with it, and says, okay, what do I do with it? DHCP gives it an IP address and a bunch of other attributes that contain certain information, and then it goes back to another system that gets all the configs download based on its location and parameters and whatnot, including ID and whatnot, and then like 10 minutes later you have the full config populated on the box without anybody provisioning. So it sort of does what the SDN should do or is going to do. They've just done it in-house doing their own tools, but that's because Bloomberg has, 3,000 developers in-house? So that's my answer. I don't know if it satisfies you, but it's all over the map. All over the map.
So something I wanted to ask about, or at least make maybe clearer, is that there are two concepts of networking that I think are at play here. One is the physical network that has ports that connect switches to switches and switches to hosts. Then there's the virtual side of it, where you have the same concepts, but as a notion of virtual switches and virtual ports. And that's sort of one of the enabling that's sort of the enabling concept that allows you to do virtual hosts to virtual switches to virtual topologies to virtual applications. And that's why I was thinking that to the questions earlier about how to enable things horizontally that may be based on a north-south protocol, but then doing your own thing. It seems like the next step in that is that a lot of vendors are saying, treat the switch as treat the control plane as a place you can put virtualized hosts, running your own systems, your own protocols. It seems like Juniper, Cisco, Arista, everyone is saying, yeah, just load software and treat it like a device that you can just add your own sauce to as needed. And these are like sort of enabling concepts to providing some of these services. Someone can do X better than some other vendor. You'll put them in and you'll enable your better firewall or your better load balancer, et cetera. But it all happens at a layer where you have your underlying network, your underlay network, and you have applications that see that part of it, but then all of your developer, administrator, whatever created virtual systems only see the overlay network where you have a virtual switch, a virtual port, et cetera, et cetera. So there's an entire layer where you can manipulate it with APIs, where you don't actually turn off a physical port or replug a physical port. You're actually saying this is an IP address, this is a port that has some magic UUID that's created. It exists now. You can use it. You can plug it into some other host. I know that's like a lot of the details, but I think that just mentioning those things might enable people to think about these as reality rather than sort of how do you turn up a network, kind of how do you create a network. So that was a bit far-ranging. I'm just throwing these thoughts out there.
So I heard everything you said, and I have some comments.
And none of it made any sense.
I have some comments on the virtualization piece, but the question for you is, what is the question? So having you said all that, what is the question?
It's not so much a question. It's something that I want to be out there so everyone's aware that you're not trying to manipulate ports on a switch. You're trying to create the abstractions of a virtual concept of a switch, which is just adding V to the name of everything in a network, and suddenly it by programming to it, people are creating virtual networks. It's
okay. So
I feel like it's just one step that everyone needs to be aware of in order to think, how do you make a virtual instance, give it a virtual network?
So I don't think that is the case.
Okay.
And the reason why is because the fundamental reason I said at the beginning, we don't run ships at the nights. There's always existing infrastructure that needs to coexist and work together with the new infrastructure. So as you're building any solutions, whatever parameters and primitives you add to the solution, it has to support the legacy equipment. You have to support legacy protocols and whatnot. So two comments there. The fact that even my own company, the parent company of Nuage is Alcatel, and Nuage is just a spin-off of Alcatel, right? They all did the same thing that Juniper did, the same thing that Cisco did, the same thing that everyone else did. And when they said about virtualizing, they said, shit, what do we do? Oh yeah, let's try our OS on VM and see what happens. Oh shit, broke. Oh no, this one, no, it works. Oh yeah, let's test it a little more. Okay, let's publish it out. Yes, we have now virtualized networking. This is what's happening in industry. So nobody has actually built the stuff with the right properties. It's just a quick answer to the market. And now everyone is rethinking that and saying, okay, this was just, okay, let's put the story out there, but now let's actually build something real. So now, okay, so how would I build my virtualized switch? Should it actually be the virtual OS running in a VM? Or should I actually maybe create two different VMs, one for routing engine and each line card have its own VM as a forwarder? Does it scale better? So now they're actually thinking about the right things and building the right pieces. So the piece of virtualization was just a quick answer to the market. This is where I stand with that. In terms of hardware, I believe once you go down the path of, I mean, even today, right, with all this, the open daylight, if you enable OpenFlow protocol on your hardware devices, anything that you do in your virtual environment, in your virtual networking with virtual switches, you can and should be doing on your new set of hardware devices, or even the old one if they support OpenFlow, using the right protocol mechanisms on the bare metal switches, talking to the bare metal servers.
Sorry, I'm going to use this mic too. What I guess I'm curious about though is that right now, some of the systems you're talking about, both Open Daylight and
OpenStack.
OpenStack, thank you. Long day. They enable pluggable networks, right? They enable the concept of a network that is built on top of another network, but more flexible. And that flexibility is what I think would take you to the ability to do less than a minute worth of provisioning in order to get entire systems to talk to each other without having to have someone run out and turn on and off ports or have to go through the risky process of changing the state of the physical network, right? And that's mainly what I wanted to bring up, is that those concepts are there. And people are doing that right now.
Okay, so I hear your point. So OpenStack is doing an effort right now to bring underlay into the overlay. So the piece that maybe I should explain myself in this is, when we talk about the hardware, we talk about the switches, right, and bare metals, we leave the data center, so the connectivity between the servers, in terms of the underlay, we leave it as it is. Okay, we build the virtual networks on top of it as an overlay, and all we do, including OpenStack that's going forward, it hasn't been done yet, but there's a lot of discussions and creating working groups on it. I'm trying to get to the slide, but okay, is that now they're making the effort to actually go and automate the provisioning of the switches and how you bring them into the overlay network as well. So what happens is that if you are still, so once you do that, all of the switches, if they have bare metal servers, they will be automated through the OpenStack to come onto the overlay, and then the switches that don't have any bare metal servers, they're totally virtualized, they're going to just serve as an underlay, and they're going to just be IP transport. So I think that will get solved. Okay, so the switches that are serving bare metal servers will get to the stage that they get automatically deployed and managed through the OpenStack. So they bring the traffic onto the overlay. When I talk about overlay, we really talk about VXLAN overlays in IP data centers, or maybe MPLS overlays. Don't know how is that going to play out. But you get into the virtual networking mode. And the switches that do not have any bare metal servers behind them, they're totally transparent. They're just running as an IP fabric, as an underlay, and they just connect your servers to the rest of the networks within the underlay. All intelligence actually sits behind it on the hypervisors, and all overlay network gets built on the hypervisor itself. Go ahead, sorry.
Are there implications for IPv6? It seems like everything is like OpenStack and everything. They always add in like 5 NAT layers to everything like that. But it seems that IPv6 seems like a natural solution, but it's always hard. But if you don't have to remember the IP address, who cares?
So in Japan, yes. Here, no. And the reason why is once you so I'll take it from the example of the service providers. If you are service providers, you do not ever need to move your network into IPv6. 125 years from now, I don't need to have IPv6 because my customer traffic is inside of my MPLS labels, and I enable IPv6 at the edges using a thing called 6PE or 6VPE, and I speak IPv6 to my customers. My entire network infrastructure can be built using simple private addresses, 10.0.0.0. So, because everything is hidden. So similarly, if you go down the path of underlay and overlay, when it comes to if you move your workloads, meaning your servers and stuff like that, to IPv6, then your overlays need to support IPv6. But your underlay infrastructure, the switches, the way they are today, they never need to be moved to IPv6. I don't know if that answers your question, but...
So we spoke at length about the scale at which an SDN controller would and would not operate in a sensible configuration. I just want to check if I've got a accurate image as to what kind of scales these things would operate. When I've been thinking about a router, I've been imagining a box, a big box, or at least a bunch of components that are physically close to each other. And when we've talked about OpenFlow, I've been imagining it as being a protocol within the router, components within a single router. So I've been kind of imagining the SDN controller together with the line cards as controlling as being the router. Is that a correct characterization?
I believe so. If you look at, let me see, where was that? Okay, so here, if you look at, for example, I would think of this SDN controller being a router and serving set of line cards, whether they are x86 line cards or they are Broadcom-based line cards, whatever they are. It installs the forwarding entries into the forwarding tables here. And then the moment I reach certain capacity, whatever the capacity is, whether it's your geographical location, so now syncing becomes a problem or something else, I put another SDN controller, and I map all these users to this another SDN controller. But the way I transfer the state between these two SDN controllers is not using a database synchronization methodologies, but using routing protocols.
Right.
For the reason of latency and sync, and for the reason of if I were to do this, the moment I do this, I need to talk to my legacy network. So I have to have something that speaks this network and the routing protocols on this side. And then I'm stuck with these gateways that have to be served, and then I end up with choking points in my network architecture. So 2 problems: the sync between the databases and isolations of the network, ships in the night.
Right. So these are effectively, as far as the routing protocols are concerned, these are now just separate routers. SDN doesn't change that.
That's right.
All right. Thank you.
And looks good. I think you're the last question, and then we're going to do the question. We're going to do the raffle, or sorry, the giveaways. Not a raffle, but trivia.
I have a question concerning security, and mostly at the user level. So over the last few years, we've seen about things like .1x and NAC being developed to make sure that someone connecting to a network is in the right network, while the right VLAN, the right subnet, and has the right permissions to access internet or other servers. Do you see any migration from those kind of bulky and weird technologies to something built on top of SDN?
I believe once you move to the SDN policy-based model, that you don't need NAC anymore, and that as that policy actually serves as a NAC because you're targeted with your own UUID, and he has his own UUID, and based on your IDs, you guys have certain network accessibility, whether that's a location, whether it's a location might. So one thing to note with this network overlays, and maybe I didn't do a good job in explaining, location becomes irrelevant because I'm building virtual networks, and typically all of the vendors, including open source community in Open Daylight, these virtual networks, they're building them with the VPN environments, so using BGP methodologies, but that's irrelevant. So I can actually build totally independent networks from the same locations, from the same physical port, just based on different UIDs. I can hide the routes, or I can even give you the same IP addresses to both of you, but just by the nature of your UIDs, you guys can be in your independent networks. So location doesn't matter. So I think once you move to this network, NAC becomes irrelevant. It's built in.
All right, that's it, everyone.
I just
Thank
made it
you.
up on the front. Thank you, guys.